talked about static and dynamic equilibrium. We're going to start doing some problems in that. We're going to understand a bit more about mass and weight, the force of gravity on an object. But before we do that, I want to go back. There were some questions that we talked about, discussion questions, that I think now you really know, but I can now test them because learning catalytics is working. So let's just start with really basic stuff. This is a review from the last two lectures, but here's the idea. A ball roll ups the ramp and then back down. Okay? Which is the correct velocity graph? Now, before I let you answer the question, when we have a problem, we're going to finish that problem that we started last time. What would you choose as the positive direction of motion in this problem? Which direction? I see thumbs going up and to the right. So naturally, you would choose a positive direction of motion upward. What would happen if you solved this problem, right? You went through some calculation and you had chosen the other direction of motion. Do you think that you would get the right answer? Some people are saying no, some people say yes. The answer is yes, and here's why. It's a convention that you choose whether you're moving positive or negative along a certain axis. As long as you keep track of the minus signs anywhere in the problem, you would get the same answer, okay? So for instance, before I ask this one again, if I was asking, I assign my direction of motion down the hill. When I roll up the hill, would that be a negative in my new axis or a positive? It would be a negative because I'm going opposite the direction of motion. Now, if you keep track of that negative sign throughout, physics doesn't care. As long as you keep track of all of them, you'll get the right answer. So we'll see this in the example in a minute. When we pick our direction of motion, as long as you're consistent throughout the problem, it doesn't matter which sign you put to it, positive or minus. Okay, so I'm going to deliver this one. We've seen this again. We've seen this several times. So go ahead and take about 30 seconds or so just to get your answer in. So which is the correct velocity versus time graph? It looks like most people are on the right track. I've got about 100 responses, so get the rest of them in. Take about 5 seconds. Okay, last few, and stop. Okay, this is really good. So 85% of you said D, that it's a linear velocity versus time graph. If I had a linear velocity time graph, what does the acceleration look like? Constant. And which sign in this case? Negative. Remember we went through this. Now, what does this displacement time graph look like? It's a parabolic curve, or a parabol, right? So, let's move on. We know this one. We've done it. You guys got it. That's great. 85% is really good. Unanimous. Perfect. 100%. Let's do the next one. So this, again, is the one we saw last time. The ball rolls up the ramp and back down. Which is the correct force versus time graph? So again, about 30 seconds. This is just review. Now when you do that, I'm going to draw something for the problem that you're solving. Okay, take it another 2 or 3 seconds. Wow, this is even better than before. Okay, go ahead and stop. So last time it was 85%, this time it's 87%. Got the right answer. But the force is down. What is the force that's acting on this object? The force of what on what? The force of, there's a rope? No, not in this picture. In our problem here, what's the force? Force of gravity on the ball. It's a negative constant, and we even solved what this value would be. It depends on the angle of incline. Okay, we talked about this last time. We'll see it again today. Now, here's the problem that we were talking about. We're going to work through really carefully. we basically had built this demonstration where I've exaggerated it here, but there was a ramp that went across the whole bench. It had a small angle of incline theta, and it had two masses. And one was little m, one was big M. Okay? And we just asked, if I let go of big M, right? If I was holding initially big M and then I let it go, what is the acceleration that this object travels? Little m. Okay? This was the problem. This is a very, very typical kind of problem about interactive systems. Now, let's go through the recipe. Before we go through calculating, what's the recipe? What's the first thing we do when we solve a problem? We draw it. Okay? We sketch out the problem. Often the problems, like you saw in the exam, are written down as a little story. You draw it. Okay? The next thing we have to do, what is our recipe for finding the acceleration of an object? This is what we've been doing. First, we apply Newton's laws. Okay? Newton's first law, second, and third law. Then we apply what? What's the other extra piece of information that we talked about? One thing we know about this problem, remember? The acceleration constraint. Right? When we have two objects that are tethered with a massless rope, they accelerate at the same value. Magnitude of acceleration is fixed. So now when we go through this problem, we first draw the picture, we separate it out into free body diagrams, we then apply Newton's second law on those free body diagrams, we then use Newton's third law to find action-reaction pairs, we then apply an acceleration. You see the recipe? We're going to go through this recipe many, many times. It's the same basic recipe, and it's going to allow us to solve a lot of these problems. And we'll see it again and again even today. We're actually going to do a lot of kind of problem solving today because these are really important to get used to. Okay, so now let me put this back. I'm going to show this to you in just a second. 1 second. Let me get rid of this so you don't see all the other stuff. Let's turn these on. .cam. Again, I'll try the center, see if it works. Okay. We did this last time, and this was our set of free body diagrams. Does this look familiar to everybody? You've seen this before. We basically have done this really carefully. We'll again work through lots of versions of this. Now, if you look at this, rather than me redrawing it, just look at what I've done. I've taken, the easy one is big M, because it's basically just two forces. And those two forces are the force of gravity on big M, or the weight of big M, and then there's the tension of the rope on big M. Right? So we went through this really meticulously with force of A on B for each one. The other thing we saw was that there was the force acting on the ramp, right? This object on the ramp. So we know that anytime there's a surface, the normal, by definition, normal means perpendicular to the surface. There's a normal force acting on this object. That's the force of ramp on mass. Okay, and we'll work with this quite a bit today. We know that there was a tension of the rope on that little mass, and we know that there was a weight pointed down. Weight is always pointed down in these typical situations. And the other thing we did is we translated these triangles. If I have theta drawn here, I can draw another similar triangle where theta is that angle between weight and this axis. Okay? Now the next thing we have to do, what's the next thing? In this case, and in any problem, the next case is to imagine what will happen. Okay? If the mass, big M, is really, really, really big, what's going to happen? Just imagine what would happen. Little mass slides up the ramp, right? It accelerates. That's the first thing you can imagine. So how would we draw our direction of motion in this picture? Up the ramp, but then I would say down the other side. I'm going to draw a direction of motion that looks like this. And this thing tells me the positive direction or the negative direction. Now, going back to what I said before, what if we assign this direction of motion, but later on we found that little m is actually much, much bigger than big M? Which, if little m was much, much heavier, which way would it slide? It would go down the hill, right? So we don't know beforehand which direction it will go. But what you do is you assume a direction of motion. If the answer comes out at the end that there's a negative acceleration, what does that tell you? It went backwards. It went opposite way you thought it would. But as long as you assign a convention for your direction of motion, you'll get the right answer. It may come out positive or negative. Do you see how this is kind of arbitrary, but it's really important to understand. If you apply everything correctly, you'll get the right answer. So going back to our diagrams, now we have a direction of motion, we have a diagram, we imagine what it's going to do, and now it's just execution by applying Newton's laws. So the first thing we did was, and let me just point this out, I'm not going to rewrite it because it's already here. The first thing we did is we went through very carefully and showed that if I imagine the center point of the rope, there's a third law pair happening right at the center of mass of that rope. The tension on the rope on little m is pulling in one direction, and there's an equal and opposite force pulling on big M. But we didn't get this statement from Newton's third law. We got this from Newton's second law. And so if you go back to your lecture notes, you'll see that. This was not the action-reaction pair, but we got this by applying Newton's third law to the center of mass of the rope. And you'll see that there's a subtle difference there, and we'll go back to it. So now, in the direction of motion, so here, maybe this makes sense a little bit more now this week than it did last week. I'm now assuming a direction of motion, and I'm going to start writing things down. In the direction of motion for little m, I'm going to write my application of Newton's law. So Newton's law basically gives us the sum of forces in the x direction, and what I'm calling the x direction here is my positive direction of motion. So for little m, I've chosen x to be up the ring, positive. So the sum of all forces, we know Newton's second law says that it's mass times acceleration. So you see that little term, mass times acceleration of the little mass, okay? And then I just add them up. There's a rope pulling me in the positive direction. That's the tension of rope on little m. But then there's a component of weight pulling down the hill. That's weight times sine of theta. Okay? So this is just taking that component that's pulling back against that mass. You see how that works? It's just sum of all forces. I set it equal to mass times acceleration. That's Newton's second law. Now I do the same thing for the big block. Okay? Now I'm going to call this the sum of forces in y, because on the conventional way is to call y up and down. But here's the trick. One thing to notice really carefully. In the first equation, in equation 1, I've assumed the direction of motion is in the way I've drawn it. The mass is going to roll up the hill, and the big one's going to fall down. If I have pieces working together, I have to assume that that direction of motion is always the same sign. So in this case, when that big mass moves down, is that a positive or negative in our direction of motion? It's positive. Do you see that I've defined the direction of motion to go down? That's what I'm going to call the positive direction of motion. So now when I apply this Newton's second law, you'll see that reflected in the sign that I've chosen, right? The sum of all forces is equal to mass times acceleration. It's just Newton's second law. Again, I've marked them as big M's. And then I have weight acting in the positive direction because it's acting in the same direction of motion. Here's the picture, right? It's acting in the same direction as the direction of motion, minus the tension of the rope on M, and that's exactly what I've written, okay? You see now how the direction of motion is how you define whether things are kind of plus or minus in your application of Newton's laws. If you keep it consistent through the problem and you do it correctly, it doesn't matter. It's a convention. The direction of motion, you can either choose positive or negative, but it has to stay consistent. And then there's this last piece, which is this acceleration constraint. We talked about this already. We know that the acceleration of the little one is equal to the big one. And so we'll call it just some random value A. It's a value. That's what we're looking for, is the acceleration. So here's some very basic algebra. We basically take equation 1 and equation 2, there. Oh, the camera got drunk there for a minute. So you take equation 1 and equation 2, and this is just a simple substitution. I know, what similar terms do you see in those two equations? What similar term is there in any of them? Do you see a matching term? Well, the masses are different, right? So the weights are different. But do you see there's this tension of rope on little m and tension of rope on big M? And we said earlier, those are the same. Okay? So all we're doing is we're using that fact, we're solving for them, and then setting them equal to one another. It's just algebraic substitution. And you get this equation, mass times acceleration plus the weight of little m sine theta equals negative mass times acceleration plus weight of big M. This is just putting together all of that information and then working through to solve for mass. So here's another step along that algebra. What I've done first is I've put all the terms with a little a together, right? This is just basically simplifying the equation and solving for a. Let me go to the next page. When I do the algebra, I get an equation that looks like this. So the acceleration is the weight of the big M minus the weight of the little m sine theta over the total sum of mass. And then again, I can simplify this even further by recalling that weight is mass times the gravitational constant g. And so I get this very compact, very simple expression that tells me how the acceleration will change depending on the angle and mass. You see? So I have the big mass, I have the little mass in there, and I have the sine of this angle. Now we can ask all sorts of questions. For instance, I could ask a question, what would the masses have to be for this thing to not accelerate at all? Right? How could I make it so it's perfectly balanced? How would you solve that problem? What do these masses have to be to not move at all? I heard mumbles. I heard like 9 different mumbles. It sounds like Death Eaters or whatever. Well, they're not the masses. So if we want to say, if they were equal to each other, it would work in very special case, right? But how would we solve it? What happens if this thing is perfectly balanced? What can we say about the acceleration? 0. I can take this expression, set the acceleration equal to 0, and solve for one mass as a function of the other. That would tell me exactly what those masses would have to be, or the ratio of those masses, to make it not move at all. Okay? So that's one thing I could ask. But let's do another one. There's a little sanity check we can do, which is, what happens if big M is equal to 0? What happens if the big mass, this one hanging here, is equal to 0? What would happen to little m? It'll just slide down the hill. Do you remember what the acceleration was when we looked at a mass just sliding down a hill? We did this calculation last time and the time before. If you plug that in, I plug in m equals 0, I get an acceleration that is just down the hill, and it's g sine of theta. This is exactly what we saw when we were just thinking of a ball rolling upward down a hill. That's the acceleration. So this equation, we've done a sanity check, we know how we might use it, but really the important part is how we got here, how to solve the problem. Okay? So the block M moves down the hill in the case where big M is equal to 0. Now, this equation gives us a ton of information. It's all embedded in there. I don't want you to remember this. I want you to know how we got there. And so we're going to go through several different examples today to kind of practice that. So let's go back. We'll come back to this in a minute. So here's today's challenges. Our goals are to continue applying Newton's laws, but now start to think a little more deeply about mass and weight and what we mean by those and how we can basically get confused in certain situations. Like, for instance, riding on an airplane or an elevator. We'll talk about it. So I'm going to flash this slide. Again, you should have this in front of you when you're taking your homework, or you're doing your homework, or you're sitting at the exam. You'll see it. Here are Newton's first, second, and third law. We know it by now. We even know how to apply them. We even know when the laws are important and which ones we have to use. We're going to start by talking about equilibrium. What does equilibrium mean? When we say equilibrium, what's the acceleration when we have an equilibrium condition? 0, right? So when you see a problem that says object A and B are in equilibrium, you immediately have one piece of information. Acceleration is equal to 0. That also means that the sum of all forces is equal to 0. We've seen some examples of this, but now we're going to use this in a little bit more of a complex set of systems. Now, remember, this is the most important part. When you start to solve a problem, you have to remember that Newton's laws are written as vectors. And so they have components x and y, And the strategy is to take this statement that the sum of forces is equal to 0 and very carefully write that the sum of all forces in the x direction are equal to 0 and the sum of all forces in the y direction are equal to 0. So immediately, just by me on an exam saying an object is in equilibrium, you immediately already have this much information. You know that the sum of all forces is 0, the acceleration is therefore 0, and you know that the sum of all forces in the x direction is 0, the sum of all forces in the y direction is 0. So I could give you that situation in a picture. You could immediately start writing down equations without much more information than that. Now, Newton's first law applies, so objects that are at rest remain at rest. We call this static equilibrium. But objects that are moving with a continuous velocity can also be in equilibrium. This is dynamic equilibrium. We'll talk a lot about both of these as we solve these problems. So let's start another example. I'm going to work through kind of rigorously so we see how these work. Here's a static equilibrium problem where it may not even tell you that it's in equilibrium. The problem never really explicitly says it's in equilibrium, so let's see if we can deduce that. You and two friends find 3 ropes tied together. Right? You were just walking through campus, and, oh, there's 3 ropes tied together. Let's see what happens when we pull on them. There's a single knot in the middle, and you decide to have a 3-way tug of war. Okay? You see who's the strongest. Alice pulls to the west. Which way is west? Quick. Good, okay, got it. We're going to call that west for now. We can assign plus or minus x, whatever we want later. Alice pulls to the west with 100 newtons of force, while Bob pulls to the south with 200 newtons. How hard and in which direction should you pull as the third person to basically keep this thing from moving? Do you see that this, without saying it's an equilibrium problem, it's saying what? The sum of forces in this problem are equal to 0. So it's an equilibrium problem without ever explicitly saying it. So let's see how we would solve this. The first thing is you draw a picture. We'll do that in a second. But you have to model it. You have to think of a really simple way to draw it. So you treat the knot in the rope as a particle with no acceleration, and the sum of forces is equal to 0. Right? That's the easiest part. That gives you a lot of information immediately. And you're going to neglect the weight of the knot. This is often a conceptual step that we have to take in physics problems. You have to assume, I don't have any information about the rope. I'm just going to assume to start that it's very light. Then you go and you draw this picture. So here's what your picture should look like, because they gave you a lot of this information. This is one of the people, I think this was Alice, pulling to the west. Then you have Bob pulling to the south. And you've drawn a little knot, and there's you pulling at some angle to try to keep everything in balance. Right? So you're kind of the omnipotent one, so you get to choose how to keep it right in balance, even though Alice and Bob are pulling as hard as they are. So here's what you do. You identify the knot at the system, so you say that's the system I care about, how it moves. Did you ever play tug of war? Did anyone play competitive tug of war? How do they mark who wins? Do you remember? There's a flag. Right at the middle of the rope, there's a flag. And when that flag accelerates past a finish line, you win it. Right? This is the same thing. You don't care about their hands or who they are. All you care about is that knot and how it gets past a certain line or whether it does. In this case, it's going to come out to 0. We've already assumed that. So now you turn this into a free body diagram. And this one is a simple one because there's only one object that we care about. We can establish a coordinate system. So for the mathematics that's going to follow, we think that it's simple to choose a typical coordinate system. X is kind of in the horizontal plane, y is vertical. We draw these 3 vectors and label them 1, 2, and 3. And then we assign an angle by convention, which is always coming from the positive x-axis. This is the convention. You don't have to choose that convention, but that's what we did. And so you establish the coordinates, you name and label each force, and what is the equation that describes how this will move? What law are we going to apply? It's second law, right? There's no interacting system. This is just the sum of all forces is equal to mass times acceleration, where the acceleration is equal to what? 0. It doesn't move. Okay? Let's work through this one. Again, really carefully. You'll see the same basic ideas we already did. But this is the problem. I'm going to leave one of these up. This is the old one. That. maybe once this gets focused, what I'm going to do is let me redraw that picture for a second on the board, and I will do the dot cam on both so that everybody can see. At least everybody has a view. The picture was really simple. It was basically three forces acting on the knot. This is the x direction. This is y. And we draw a big compass. So we said, I think this was 1, 2, that's right. Check. Yeah. Okay. So in an equilibrium problem, we know that the sum of forces is equal to 0. We can immediately get information from that. So written up here already, I see that the sum of all forces is equal to 0. That immediately allows me to start writing this equation down. Basically what I'm writing here, let me get this paper out from under. Hard to see. There you go. So all I've done is like brute force calculus. I take the sum of all forces, the net force in the x direction, defined by my picture. I see that I have the x component of T1 plus the x component of T2 plus the x component of T3 equals to 0. What is the x component of T2? It's 0. But I still wrote it. I wrote out every x component. Then I go back and I say, oh, this one's only pointing in y. So ultimately, that's easy. I can take that one away. The x component of 1 is really easy. It's just negative T1, the magnitude of that vector. And then the T3 is the one where we have to worry about the angles. We have to find that projection. We'll do that in a second. But you see what I did is I just put in everything to start, and then I said, which ones don't I care about? Which ones do I need to find? I'm going to do the same thing in the y direction. So the sum of forces in the y direction are T1 sub y, T2 sub y, T3 sub y. What's the y component of T1? 0. So immediately you start kicking out the ones you don't care about. T1 is only in the x direction, and so I can immediately scratch that one up. So what I would suggest when you're solving these problems, write them all out first, then systematically go through and do it. Don't just skip those steps. It's actually really easy for you to miss things if you don't take it kind of carefully. Okay? So now from the free body diagram, we can start writing out these components. And this is just a way of kind of longhand writing these things down. The first one I can do is I can say that T1 is in the negative direction, and the magnitude of that x component is just the full value of T1. So T1x is minus T1. The magnitude of T2 in the x direction, we already said, is 0, so I just wrote it down. The magnitude of 3 in that direction is the magnitude of that vector times the cosine of theta. Because wait, this is a bad trick, but I'm going to teach it to you anyway. I always have weird ways of remembering things. If I have an angle like T3, and I have the x-axis like this, maybe you've heard this one. If I shut my mouth on that angle, is it sine or cosine? It's cosine. If it's a shark mouth, and I shut my mouth onto the x-axis, it's a cosine. It always works. I've used that since I was about 12. Okay? Keep it in mind, and you'll prove it to yourself if you write it down carefully. Okay, so coming back to this, T3 cosine theta, it shuts its mouth on the x-axis. It's a cosine. If it opens its mouth on the x-axis, it's the other one. See how it works? It's a sharp. Anyway, don't use it if it confuses you. Here's the other one. So the tangent in the y direction is 0 for number 1. We already said that. The tangent for T2 is negative, so it's going down. And then the T3 is just the sine of theta, just like we said. Okay? Is everybody straight on this part? You've had a lot of practice with this, so you've seen this work before. Now we can just put these into our equations, and we simplify. So I'll do one at a time. Here's basically Newton's law applied to the x direction. I have minus T1 plus 0 plus T3 cosine theta. I know that it's equal to 0. It's equilibrium. And that gives me an expression that T1 is equal to T3 times cosine theta. right? Just algebra. Then I go and I do the next one. So again, Newton's law in the y direction gives me another expression. 0 minus t2, we see t2 goes down. T3 sine of theta is the y component of t3. And I get another expression, t2 is equal to t3 sine theta. Okay? Can everybody get to that point? That's just application of Newton's second law. Here's an algebra trick. Now what I'm doing is the problem was asking what does t3 have to be in order to balance t1 and t2? I'm going to do a little trick. I'll give you this trick and you'll never forget it if you practice it. There's a really easy way to solve this problem. Here's what we're after is t3 and theta. Do you remember this from algebra? We have two equations in two unknowns. Do you remember that? If I want to solve for some variable in an algebraic problem, I have to have the same number of equations as I have unknowns, or I can't determine it. Here you have two equations, exactly two unknowns, theta and t3. T1 and t2 are what Alice and Bob are pulling. There's a really simple trick, and that is to find the angle first. Does anybody see the trick yet? Trig identities. You know trig identities, there's a really important one which you've learned, is that if I take the tangent, it's the sine over the cosine. If I just take those two expressions and I divide this one divided by that one, I get t2 over t1 is just t3 sine theta over t3 cosine theta. The t3's cancel out. I then get an expression of tangent theta is equal to t2 over t1. Can you solve that on a calculator? If I ask you to solve the inverse tangent of t2 over t1, you immediately get the angle. Okay? Once you have the angle, you then just go back in and you plug it in here, and you'll get the magnitude of t3. Okay? Really straightforward algebra trick. It will save you tons and tons of time, and it will make far fewer errors than kind of using your calculator to turn these numbers. So I'm not going to give you the rest because it's just getting numbers in your calculator. It's just that theta is the inverse tangent of t2 over t1. Once you calculate that, you plug it back in, and you get t3. Okay? So now you have the way to do it. I'm not worried about the numbers right now. Now let's go back. Again, any questions so far? I'm working through. You see the recipe though. The recipe is draw the picture, imagine the motion, draw free body diagrams, Newton's laws, acceleration constraints. Do you see how it's just the same recipe? You're going to work on this a lot as you go. Here's another one. This is a pretty simple one, but it can be really confusing. I want you to try this in your groups, in your discussions. So a cart that can roll freely sits at rest on an inclined plane. And there's a little wall there that doesn't allow it to move. Okay? The cart's weight is W. What is the magnitude of the contact force acting on the cart due to the barrier? So I'm going to deliver this problem. I'm going to give you 2 minutes. Draw the picture, draw the free body diagrams. If you're thinking ahead, you'll see another problem in a second that will ask for more information. So if you do it all carefully now, you'll find that you already have the answer for the next one. So sit down, draw this picture out, take your time, we'll do about 2 minutes. And the basic question is, what does the force of this barrier have to be on the cart in order to keep it from moving? Now, I have one other thing to say. If we imagine this motion, what would the motion be? If that barrier is strong enough to hold it, what's the motion? Is it in equilibrium or not? It's in equilibrium. It's not going to roll. Which way would it roll if I moved the barrier? Down the hill. And we know what that acceleration is. It's g sine of theta. We've already done that. So think about it. See if you can draw the free body diagram super carefully, work through, and get, with a really careful drawing, can you get the right answer? And again, you'll see that we're going to ask the other questions about this problem, so if you do it all in one go, you'll get everything at once. I'm not going to show you that yet. Okay, good. It didn't work. So I have 14 responses. You have about another minute, though, so make sure you draw everything. Draw free body diagrams first. Challenge your neighbor. Ask them what they got. See if you're getting the same drawings. And the question is, what is the magnitude of the contact force acting on the cart due to the barrier? So again, the steps are draw the picture, imagine the motion, apply Newton's laws. Do we need Newton's third law in this one? Maybe. Do we need Newton's second law? Probably. We're in equilibrium. So go ahead and take about 20 more seconds. Try to get an answer in. I've got a lot of answers already. About 70, so about half. Okay, about 10 more seconds. Okay, I'm going to stop this. I'll pause it. We'll come back to it. So here's what I've got. I see that basically it divides into three answers all equally the same weight. So we do not know yet how to do this. What do we do? What's the first step to do it? You draw a picture. Okay? We have a pretty good picture there, but let's draw it first. We'll see if this will clear up any of what we're saying and what we're doing here. Here's my version of that same picture, just drawn a little bit more carefully. You see that? Yeah. All I've done is taken that same drawing that was given in kind of a very simple form, and I've added some detail. So here's the cart, here's the barrier. There are lots of different forces going on. Remember, what are the forces that we most think about? The first one is this object has weight, W, right? There's another one, which is, what's this one? What do we sometimes call this? The force of ramp on cart. What do we call it? The normal force, okay? Then there's the force of cart on ramp, but this is not Newton's second law. This is a third law pair. There's a force of ramp on cart and cart on ramp. Now, what other forces are missing from this diagram? There's a whole important set of forces on here. Anybody have it? Exactly. So now you have the barrier and how it interacts with the cart. This is what we're asked about. So we have to draw a vector that is the force of barrier on cart, and we can draw a vector that's the force of cart on barrier. And by Newton's third law, those are equivalent. And we know it's in equilibrium. So if I do that, I'm not going to draw them here because we'll see them in a second. But basically, we know that the force of the ramp on the cart is equal to the force of the cart on the ramp. But we also know, equivalently, that the force of the barrier is equal to the force of the cart on the barrier. So the force of barrier on cart is equal and opposite to cart on barrier. So take this. Now you have these vectors. You have the angle drawn. If you see, I've drawn theta here, but then I have a similar triangle right here. See if you can answer the question, which we said. Let me just put it on one side. The question was basically, what is the magnitude of the contact force acting on the cart due to the barrier? Once you have this drawing, you should be able to read it off almost immediately. Let me clear the board because I'm going to draw this. Okay, keep going for about 10 more seconds. Okay, get your answers in and stop. Let's stop here. Okay? Let's think about this. Stay with me for a few more minutes. Here's what we want. We're asked about what is the force of the barrier on the cart. So Newton's second law tells us that we only care about what's happening at the cart. So let's draw a dot, which is the cart. Let's draw the forces on that cart. What's the main one that we know? This is the force of gravity on cart, which we'll call weight. Okay? Now we have an angle, and I'll draw this to match the picture that I have at the right. There's this angle because of the triangle. That angle that I've drawn is right here. We have a normal force. It's from the ramp onto the cart. So let's even call this force of ramp on cart. And there's a force pointing this way that is the one that we mentioned before. This is the force of, we'll call it barrier on cart. Are there any other forces in this picture? I don't know of any, right? We don't care about friction. It's not moving. It's in equilibrium. How do I find the component of this weight vector in this direction? I heard it. How come? Why do you say so? Because the vector closes its mouth on that axis. The other way you can do it is draw a triangle and prove it yourself. If I close across the angle, this is weight times the cosine of theta. What's the component of that vector on the other axis? It's got to be weight sine theta. So there are these projections of the weight vector in those two directions. Which is the third law pair that gives us the force of barrier on cart? The force of barrier on cart is equal to the force of cart on barrier, which is equal to weight times the sine of theta. Do you see that? In the direction of motion, these two forces have to equal out. So what's the answer? It's A. Okay? Now, let me go to the second one. You should be able to answer this immediately. What is the magnitude of the contact force acting on the cart due to the ramp? What's the contact force of ramp on cart? It's this normal force. What's the magnitude of that force to keep it in equilibrium in that direction? It's the component of the weight. So it's weight times the cosine of theta. Which answer is this? B. Okay? Does everybody see? All we've done is basically take the projections of these different forces and apply Newton's second law. Okay? So let's skip this. This is what we've already done. Now, here's a question we can ask. We're going to end on this one. If I pull that barrier out of the way, which way does the cart roll? Down the hill. What's its acceleration if it does that? G sine theta. We've already seen it. This is exactly what we see before. If you look at our answer for a second, you see that this force that's holding it there, weight is m times g, and there's a sine theta. It's the same basic thing that we saw in that previous problem. The projections of those two vectors perpendicular to and in the direction of motion. Okay?